I'm trying to record it now. In a voltage divider biasing, you have a BJT standard, you have a collector resistor, you have an emitter resistor. That is standard everywhere because you need that collector resistance and you need that emitter resistance as well. In a voltage divider biasing, using the same supply voltage, we are going to generate a voltage at that point, a DC. And that DC, we are going to call it VBB. That is your positive supply voltage. This could be a ground or even a negative supply voltage. And this voltage, that is what we are going to talk about. This is basically a Thevenin voltage. We will see that in detail soon. The process of establishing a constant DC in the collector is called biasing. The collector means establishing a collector current. Basically, collector current must flow through the collector to the emitter, through the emitter resistance to the ground or negative supply voltage. A well-designed bias scheme must be calculable, predictable, and insensitive to variations in temperature and beta. Then we also need to place the bias point in the middle of a transfer curve where maximum signal swing is permitted. So I want to explain what is this maximum signal swing. You are working with a positive supply voltage. You are working with a negative supply voltage or ground. That is your positive supply voltage. Your output is taken from the collector. What is the DC at the collector? We call it voltage at the collector. Okay. If you keep, this is the voltage at the collector. This is where you take signal coming out of the BJT. Okay. If you want maximum signal swing between a positive supply and a ground, let's assume it is a ground. This voltage at the collector must be exactly in the middle. Assume this is a graph. Origin. You keep the voltage at the collector VC exactly in the middle so that you can have all the swing in the positive and equal amount of swing in the negative direction. That is the maximum signal swing that we are expecting. Or mostly that is what we are looking for. Where we will end up, we will see soon. Okay, place the bias point in the IC VCE line. IC-VCE such that maximum signal or desired signal swing is permitted. Okay, we will see that. I gave you a hint. What is signal swing? What is the importance of that? Now, voltage divider biasing. We are going to choose VBB very much greater than VBE for improved bias stability. What is this bias stability? Bias stability is something very important. Bias stability means once you set the bias, it must stay like that for the entire operation of the BJT. It should not even shift. Nothing must affect the stability of the bias point. If you need bias stability. This is the rule of thumb that we are going to choose. VBB very much greater than VBE. But this will reduce the amount of voltage swing at the collector and result in lower voltage gain. We will explain the second part later. I will try to explain the first part now. See, going back to the camera. Okay, this is the emitter. You have a VBB, so that voltage at the collector must be around halfway from the ground. And VBB needs to be very much greater than VBE. VBE is like 0.7. So VBB, we are looking greater than or equal to 10 times 0.7, that is 7 volt. We are looking for a VBB around 7 volt. Okay, it doesn't look that bad, but nowadays there are many of electronic circuit that is working at 3.3 volt. The latest technology allow 1.5 volt. Okay, so this is a very difficult to attain situation. VBB having such a high voltage is nearly impossible. So what you do, we need compromises. So we are trying to keep VBB very much greater than VBE. At the same time, we need a compromise, and that is called the compromise. On engineering terms, we call it design trade-off. That means we are gaining on something, compromising on something else. So we are going to choose, this is the compromise we are going to choose. We are going to choose voltage across RE around 1/3 VCC. And okay, let's try to see that what exactly it means. Okay, let's say VCC is 12 volt. So we are going to choose voltage at the emitter 12 divided by 3 around 4 volt. Voltage at the emitter is 4 volt. Voltage at the base is going to be 4.7 volt. That is for a power supply of 12 volt. Okay. Now look at what is the VBB we have. Is it very much greater than VBE? Not strictly. Strictly, it must be around 7 volt, but we cannot afford that high voltage. We are compromising on the voltage. Okay. Okay. The second is choose RE very much greater than RB over beta plus 1. Okay. I did not explain what is RB. RB is, okay. Let us say what is VBB. VBB is Thevenin voltage. VBB is Thevenin voltage at the base at this point. What we do is we open circuit there. What is the voltage at that point? That is called Thevenin voltage. So VBB is, how do you find? If you open circuit, I am going to call it R1, this one R2. So if you have an open circuit at that point, This is just a two resistors connected in series, and we call it as a voltage divider. So VBB is the open circuit voltage at the base. This is going to be VCC R2 divided by R1 plus R2. That is the voltage divider expression. Then what is this RB? RB is Thevenin resistance at that point, R Thevenin. How do you find R Thevenin? We ground all the power supply voltages. That means this is going to be a ground, that is already at ground. Now R1 and R2 are in parallel. R1 parallel R2 is R1 R2 divided by R1 plus R2. Okay, this is Thevenin voltage. This is Thevenin resistance. Thevenin voltage and Thevenin resistance are seen at the base. Okay, now we are going back to the slide. Okay, to make the bias current IE, or basically IE is approximately same as IC, insensitive to variations in beta, RB must be made small. RB is R1 parallel R2. Lowering the values of R1 and R2 will increase currents I1 and I2, resulting in reduced input impedance. We will describe that in detail soon. Okay, currently you need to understand there is a design compromise that we are going to choose. Choose I1. I1 is current through R1. Remember in the diagram, I1 is the current through R1 around IE over 10. So choose the current through resistance R1 around IE over 10. So current I2 is I1 minus IB. Okay, I will explain all these things in the next slide. You will see all the currents. VCC, RC, RE going to ground. Okay. Current through RC is called IC, collector current. Current through RE is called emitter current, IE. Okay. Then current through R1 is called I1. Now take a KCL at this point. One current is coming in, two currents are flowing out. That basically means I1 equals IB plus I2. Or basically, you can say that I1 minus IB is I2. So in this way, you can find current I2. And all the expression we wrote, they are also here. VBB is voltage divider expression. Voltage, that is the Thevenin voltage at the base. RB is R1 parallel R2. Okay. If you have this much, then we can simplify this current circuit. How? Let's see that. We will go back to the camera and show you that. We did up to Thevenin voltage, Thevenin resistance. Thevenin voltage is VBP. Thevenin resistance is RB. So what do we have? We can make a Thevenin equivalent circuit. This is called VThevenin, or that VThevenin same as VBP. Then there is an RThevenin. RThevenin same as RB. Okay, this voltage divider that we did here, at this point we found VThevenin and then we found RThevenin. Now we are trying to replace R1 and R2. Then there is a base, there is an emitter, and there is an emitter resistance. So we are trying to make a Thevenin equivalent circuit for this much. That this much is replaced with a Thevenin voltage in series with Thevenin resistance. What is left is the base and emitter, and an emitter resistance going to ground. So if we replicate that using Thevenin voltage and Thevenin resistance, we have VThevenin in series with RThevenin. There is the base. Here is the emitter. And here is the emitter resistance, RE. So we have a closed circuit now. In a closed circuit, there is a current. There is always a current through a closed circuit. So from this closed circuit, we can make a KVL expression. How is this KVL expression is going to come? Start with the battery. Go into the direction of the arrow, like that. Negative to positive. It is positive. We write VBB. We are going in the direction of current, so there is minus sign. What is the current through that resistance? That is same as base current IB. VBB minus IB times RB. Now, this is an NPN transistor. We have a VBE between base and emitter, with that side more positive than this side. Therefore, we go in the direction from positive to negative. It is negative sign minus VBE. So we started with VBB minus IB times RB minus VBE. Then current through that component, emitter resistance, we call it emitter current IE. So again, minus IE times RE. We complete the loop. There is no other component until the negative side, equal to what is KVL says, algebraic sum of all the voltage equal to 0. VBB is a voltage. Current times resistance is a voltage. VBE is a voltage. Current times resistance is a voltage. Algebraic sum of all EMF equal to 0. From here, what we say, we move all the current to the other side. Basically, we get VBB minus VBE equals IB times RB plus IE times RE. Now we have VBB, we know how to find it. We have found it before, VCC R2 over R1 plus R2. VBE is We are assuming it's a constant around 0.7. That is a base current. We don't know. RB, R1 parallel R2. Emitter current, we don't know. So this is one expression, two variable. But we know. What do we know? We can replace IB equals IE over beta plus 1. In this case, we can simplify this expression. Let's replace. Left-hand side remains same. On the right-hand side, I am going to replace IB with IE over beta plus 1. So IB is replaced, but we have an RB as well. Now we have a common factor on the right-hand side. IE. Take it out and make it a common. IE times RB over beta plus 1 plus RE. Or in other words, IE equals VBB minus VBE divided by RB That is how we can find the emitter current. Time for questions. I want some of you to ask me a question.
I say on my side, I'm good.
All right. So, what we did so far is we made something called voltage divider bias. In a voltage divider bias, we have certain benefit in comparison to all the other types of biasing scheme. What are that? We have improved bias stability. We have improved bias stability. That is, once you set it up, it is going to remain like that. And we have bias current insensitive to variations in beta. And we also have calculability. That means we can calculate and find out. And we have insensitive to variations in temperature. That is going together with bias stability, and less sensitive to voltage. So all the points that we have discussed so far are achieved using voltage divider bias. Okay, considering placing the bias point in the IC-VCA curve such that maximum or desired signal swing is permitted. We did not get maximum signal swing, we have desired signal swing. We will see that as soon as we go down to voltage divider bias. Okay. What we are going to do is take an example. We have a voltage divider bias here, 15 volt supply voltage, R1, R2, RC, RE. How do we analyze? We go according to the sequence we learned just now. First, we calculate VBB. Then we work out RB, which is R1 parallel R2. Then we work out emitter current. And again, one more assumption. When beta is very much greater than 10, this is going to save you a lot of time. Collector current is nearly same as emitter current because we work out the emitter current directly using voltage divider. Okay, voltage at the collector is VCC minus ICRC, which remains same. Voltage at the emitter is negative supply voltage times, remember, wherever you see IC, we are allowed to use IE. VCE is VCC minus IC times RC plus RE. Now we will take this same problem and we are going to work out. Now what you need is a calculator with you now. First, let's make the diagram. RC, RE, that is R1, this is R2, ground, 15 volt, RC is 5K, RE is 3K, RB1 or R1 100K, RB2 or R2 50K. Okay, BJT has a beta of 100. Beta 100 means beta is very much greater than 10. So we are basically going to say IC nearly equal to IE. Oh, sorry, nobody even reminded me that I wasn't sharing the camera with you. This is what I did. BJT with 5K, 3K diameter, R1 is 100K, R2 is 50K. Beta is 100. That basically means beta is very much greater than 10 and IC equal to IE. How do you find? Number one, we start with VBB. VBB is VCC R2 over R1 plus R2. That is 15 times R2 is 50K divided by 100K plus 50K. This is same as 15 times 50 divided by 150. 50 over 150 is 1 over 3. 15 over 3 is 5 volt. Do you agree?
Yes, sir.
Next point is RB equals R1 parallel R2. That is 100K times 50K divided by 100K plus 50K is 150K. Give me the answer, please. It must be like
33.33
unit.
kilo ohms.
So we found RB. Now we can make the expression for collector current approximately equal to emitter current. How? VBB minus VBE divided by RB over beta plus 1 plus RE. That is 5 minus 0.733.3K divided by 101 plus RE, which is 3K. This is 4.3 divided by, give me the answer there, please.
Zero 0.33. Mhm.
1.29 milliamps. 1.29 milliamps.
That is your collector current. Okay. Once you get the collector current, you can find all the voltages and all the other currents. If you want base current, you can work out that as well. But base current is not going to be important in most of the calculations, because collector current we are going to start with. This is the most important value that we need. We will start working out from there. Only one thing probably that we might need here is VCE. That is to ensure your BJT is operating in the active region. VCE is VCC minus IC times RC plus RE. Remember, we are assuming same current is flowing through collector and emitter. Why? The difference is too little. That is the reason. For example, say 15 minus 1.291 milliampere times RC plus RE. 5K plus 3K is 8K. Work it out for me. VCE equals
4.68 volts.
we got somehow 4.67 volt. Fine. So VCE, look, what is 1/3 of VCC? VCC is 15. 1/3 of 15 is 5 volt. You are getting 4.67, very close. So all the assumptions are satisfied in this calculation. Time for questions.
Sir, I have a question, but it's not based on this answering. It's the maximum signal swing. I'm not completely sure what that is. Can you maybe explain that again?
Okay, we will go back to that
Thank you.
sooner than later. Okay, let's see. Let's go back in there. Let's find what is voltage at the collector. That is VCC minus IC times RC. I believe all of you will agree to that. That is 15 minus 1.291 milliampere times 5K. What is the voltage at the collector? This is the voltage at the collector. This is the voltage at the collector. Go back to the diagram. Do we know what is the voltage at the emitter? Voltage at the emitter is easy. Why? Well, you subtract 0.7 from VBB. That is, VBB is 5. 5 minus 0.7, it is 4.3. So voltage at the emitter is 4.3. Voltage at the collector is 8.5. Now, let's make a graph. On the X is time. On the Y is your voltage. Let's say, what is the voltage at the collector? Voltage at the collector, I'm going to mark it like that. Voltage at the collector was how much? 8.54. This is 8.54 volt. What is the voltage at the emitter? Voltage at the emitter, let me mark it like this. .3 volt. Now, what is other point? Important point is your supply voltage. How much was it? 15 volt. That is your VCC. This is voltage at the collector. This is voltage at the emitter. So from 8.54, this signal can swing up to 15 volt. Or the positive signal swing is 15 minus 8.54. What is the negative signal swing possible? 8.54 minus 4.3. Do you understand that much? Do you understand this much?
Yes, thank you, sir.
Or in other words, in this case, 15 minus 8.54. This is like 6.5 volt. Next, remember, this is voltage at the emitter. If the signal, this is like signal swinging from 8.54 that way and swinging in the reverse direction like this. Okay, remember, we need equal signal swing. So if you really want maximum signal swing in this case, your VC must be selected exactly in the middle of these two. And again, we may need to leave a VCE equal to 0.3 so that BJT will not enter into saturation. More I say, more you get confused. Are you all fine with this?
So can you please go over it one more time, sir?
Which point you want me to go? You understand VC equal to 8.54. VCC 15. Voltage at the emitter is 4.3. Do you understand all the three?
Yes, sir, I understand the 3 points. I'm saying on the part of the graph with the, because aren't the two sides supposed to be equal, the top part and the bottom part?
See, every signal that we receive are perfectly symmetrical. Whatever positive must go, whatever negative. Otherwise, signal will be distorted. Do you agree?
Yes, sir.
So, whatever positive signal swing must be available on the negative as well, same amount.
Yes, sir.
So, this one and this one must be nearly equal. How do you get it? Remember, looking at, we selected VE approximately 1/3 VCC. And we usually choose this one 1/3 VCC. So between collector and emitter will be 1/3 VCC. So if you choose this kind of arrangement, 1/3 VCC across RE, 1/3 collector emitter, 1/3 across RC, you may get this kind of an idea where positive swing is nearly equal to negative swing.
Okay, sir, thank you. I see. I was just confused because the calculations I ended up getting when we add the extra 0.3, it was only 4.54 and wasn't close to the 6.5 that we got.
Okay, it will go 0.3 less.
Okay, sir.
So this is about signal swing. Okay, it's not that highly critical about signal swing. It must give you a fairly good understanding how a BJT is operating. Okay, so we have all these things worked out, and if you click on that, it will take you to a YouTube page where all these calculations are done exactly the way we did. Can we move on?
Yes, sir.
Okay. Now, before going into this slide, this is going to take a while. So I'm going to stop this class at this point. Now, what I want you to do is choose the same problem. Change the VCC from 15 to, say, 12 volt. And choose the value of beta different, say 150 or maybe a 200. And repeat the same problem again and again and again. If you can do it 10 times, you will get 10 times more insight into operation of a BJT. Okay. After this, what you could do is go to your LT Spice. Now I'm going to open some common emitter. Okay, there is one. This is a BJT amplifier. Can you see the LT Spice screen now?
Yes, sir.
Okay. This is one of the circuit that I did before. Okay. You see a capacitor there, another capacitor, another capacitor. Leave it. Just take this problem and work, and you can work it out by yourself. Find VBB, voltage emitter, VCE, current through collector emitter, and the beta of this one you can assume it is 200. Okay. Once you do this calculation, then you can build up a circuit like this in LT Spice, and you can do the DC operating point simulation. DC operating point simulation is, we have done DC operating point simulation before, I believe. Go to simulate, edit simulation command, choose DC operating point. You get something like that. Okay. And it is coming here. Then you just press run. Here you will get all the voltages. Voltage at node 2, this is node 5, node 7, node 1 is 12. Node 1 is always, node 0 is ground, node 1 is VCC, and all other nodes. There are only 6 nodes identified. Then you can see IC Q1, IB Q1, IE Q1, and these are current through all the resistors. Okay. You can also see, also once after simulation, you can put that icon on top of your RC. Look at the bottom left corner. Can you read what is there? Bottom left corner of the screen. Can you see it?
Yes, sir.
It is saying right click to edit R1. Okay, we don't need it. DC operating point, IR1 equals 1.5027 milliampere. And it also says dissipation, that is power dissipated in that. You go to the BJT, look at the bottom. Power dissipation, it shows, but we need collector current. What you do is that is the node voltage of the collector. I'm trying to see the collector current. Okay. Okay, collector current will be same as current through R1, 1.5 milliampere. Now you can see current through the base, 4.8 microampere. That is current through emitter, 1.5075. What is the voltage at the collector? .5027, slightly less than the emitter current. You can see that. So all the calculation that you do with a BJT, you can also do simulation and verify what the answer you must get in the calculation must tally with what the simulation is saying. Remember, simulation could be it's like 10 order of magnitude accurate than what we do, but we will see almost the same result. Okay, that is the assignment for you to do over by today evening. Okay, I'm going to stop the class for now. Just now, I'm going to stop it. Bye, thank you. Are there any questions?